In Chapter 9, we are going to talk about two-way slabs. And those types of slabs are the slabs where the aspect ratio um, makes the load path for the load goes in the two different directions, in the x and in the y. Why is it going in both directions? Simply because the aspect ratio of the short span to the long span is between 0.5 and 1, which means the longer span is less than double the shorter span. And in this case, the load will transfer in the two orthogonal directions that is provided within the slab, provided that on each side we have a support. So that means we do have a support here, we do have a support here, and over there, and on that side. So long as we have supports that can absorb those loads and take them, transfer them down to the columns, then the choice of the load is to go in the two directions. These two directions, we're going to call them one as the short and the other one as the long. And as we go, we might get into the case where both of them are exactly the same, then it is equally distributed in the two directions. A quick introduction about the types of two-way slabs. Within those types of two-way slabs, we have something called the flat slab, where the load will be transferred directly from the slab to the columns, but still in the two directions. Those flat slabs could have really heavy loadings that require that we have something called the drop panels or the column heads or capitals. Those provide higher resistance to punching shear failures. Also, we have the waffle slab, where instead of having just regular slabs, when the slabs have higher spans going to 7.5 to 12 meters, then we start providing those ribs, and those ribs are much stiffer elements within the slab itself that takes the load in two directions. And then finally here we have these slabs with beams, or what we call the solid slabs. Those are very commonly used types of slabs, which is basically slabs that are surrounded with beams, and then those beams are the stiff elements that take the load down to the columns. So it's kind of a clear load path for the load from the slab down to the columns. Back to this, we can take a quick look on the different span length which are considered economic for flat slabs. We have between 4.5 and 6 meters. Waffle slab can go higher, all the way to 12 meters. Flat slab for heavy industrial load can take up to 6 to 9 meters. So the ones that we just looked at here. And then finally, the ones with moderately loaded structures, just like buildings and other structures. This is within 6 meters spans, 6 to 7 meters max. Would be very economic to use those solid slabs. What's the behavior of the two-way slab? And I encourage you to go back to the video of the one-way slab, where we describe the differences in stiffnesses between the short and the long span, and what makes the short span take higher load than the long span. If we get into the two-way slab behavior, that before cracking, the slabs will act, or they generally act, as an elastic plate. That elastic analysis can be used to calculate stresses and deflections. After cracking, which most probably will happen at locations of highest moments, and for this we're most probably talking about edges and mid-spans. So edges would be the highest negative moments, and then mid-spans would be the highest positive moment. So those are the main three locations where we could possibly see those cracking happening. And so those cracking after they happen and before yielding of steel, the slab is no longer isotropic, which means the two different directions are not working in the same behavior. And then flexural stresses are reduced. And then, however, the elastic analysis can still be giving us adequate results. How it looks like, you'll see in the stage A, as you load it a little bit higher moment, negative moments are at the sides of those slabs within the short direction. And then as you progress with loading the slab, those cracks will propagate more, and then the cracks for the positive moment at the bottom of the slab can be introduced. Same thing can happen on the other side because of the long direction loading as well. And then those yield lines start to connect together, forming that nice triangular and trapezoidal shapes, which is very commonly used for the distribution of the load of this slab on those beams. So this is how the final shape of a regular rectangular slab would have reached during the failure. Going to the analysis, when we are analyzing slabs, generally speaking, we're talking about those strips. And those strips that we are concerned with are the strip in the short direction and the strip in the long direction. Now, the coefficients method that we will be talking about today will address a very simple way to calculate those stresses based on calculating moments in these two different strips, and based on those moments we can find the reinforcements in the two directions. But generally speaking, how those two strips behave in strip A and B and C, we will see that the deflection within, for example, strip B and strip C will be the same deflection at the midpoint, because they both have this point in common, that point here. And then based on the fact that we have the two strips exhibiting the same deflection, while we have strip B higher stiffness, or contains a higher stiffness than strip C because of the length, then definitely the strip B will get a higher force than the force taken by strip C. That's why we say that the short direction in the two-way slab takes higher load than the long direction. Going to the analysis method, I want to say that the most commonly used analysis method for a two-way slab currently in the market is using computer programs. So people would go to SAP 2000 or SAFE or any of those, SAP 2000 or SAFE program, which is also one of the CSI products that people use to analyze those two-way slabs and find the stresses and then reinforcement. But then in the old days, we used to have those nice methods that are very important to understand, especially to be able to verify what the computer program is giving us. We will study today with us the coefficients method. The coefficients method is one of those very simple methods that people have used in the past and still use it to quickly find the stresses and the moments within a two-way slab. Now, some conditions will have to apply to be able to use the coefficients method. What are those conditions? Number one is that it has to be two-way edged supported slab, which means that in all the edges of the slab you have to have beams or anything similar to beams that we can say that they are considered stiff enough. So this is what I'm talking about. On each edge of the slab we have to have some edge, some member that can take this load. Okay, and now it has to be stiff enough. This is the first condition. The second condition is it has to be stiff enough. And when you say stiff enough, what do you mean? It means that my height of the beam, my depth of the beam h, needs to be at least 3 times h of the slab or more. Okay, so the least amount, or the smallest ratio between h of the beam, height of the beam, to the height of the slab is 3. Why do you need this condition? Is to call it a stiff beam. Then what if I don't have this? What if I have a really small beam that is not as stiff or as much as stiff or strong enough to be called a beam? In this case, we will simply see that the behavior of the slab is to take the load directly, because the slab now becomes stiff enough. It will take the load directly to the column without counting on the beam. And then the load path in this case will not be the clear, nice load path that we all want and desire for our two-way slab. And then the third condition is that the design of such slabs follow the provisions of Method 3 in ACI 318-63 code. Remember that those beams could be stiff RC beams or steel beams as well. And in this case, when we talk about steel beams, we also talk about that nice ratio of EI for the beams divided by EI for the slabs. Okay, so we can also still conduct this nice relationship between two different materials. In this case, we don't have to only count on H over H. We then involve the modulus of elasticity and the I, which is the moment of inertia for both sections. Now, within our coefficients method, we will have to understand the edge support or the conditions, which ends up giving us the cases. We have what we call these 9 cases of end conditions for 9 different types of slabs that we will use to be able to obtain our coefficients. To understand those, we need to understand very important concept, and this important concept is the edge condition. So we have 2 types of edge conditions, either continuous edge or discontinuous edge. I want you to remember those two. So how do I know a continuous edge? It is simply the edge of a slab that is connecting the slab to another neighboring slab. We definitely would want it to be a continuous condition, because we will provide negative moment reinforcement here, so top reinforcement, which will make the condition here a continuous condition, which means we have negative moment between these two slabs. So once I see that this slab is attached to another slab, that means it is a continuous edge. If it is not attached to another slab, that means it's the edge of the whole slab, that means the end of the slab itself, then it is a discontinuous edge. So for the discontinuous edge, if we're going to draw this slab, imagine together that we're just going to draw this slab with the condition, we will simply draw the ones that are going to be continued with a neighboring slab with such a hatch. So this here is a continuous edge. And we will draw the ones like this one here being the edge and this one here being the edge. We will draw them without the hatch. So in this case, this will become the discontinuous edge. And then for every slab of those, we can do the same thing. So for example, the one in the middle here, it is continuous in all directions. So in this case, we just hatch all directions. And for the one over here, it is continuous on 3 sides, the top and the left side and the bottom side. Here's the top, the left side, and the bottom side, because it is attached to 3 different slabs. And then on the side where it's the edge slab, it is considered like a discontinuous edge. And then we will talk about, we will take this as the first step to be able to find our cases. So if it is, for example, not connected to any of the slabs for all the sides, it's case 1. It is connected to slabs all sides, it's case 2. From 2 sides that are the short side, it's case 3. 2 sides that are adjacent to each other, it's case 4. Case 5 is connected in the long direction and opposite sides. Case 6 is connected to only one side while it's the long side. Case 7 only one side while it's the short side. 8 and 9 connected from 3 different sides, while 8 is 3 different sides with the long side being discontinuous and the short side being discontinuous in the case of case 9. So if we want to take this as an example, looking at the one in the middle here, it will be the one that has continuous from all sides. I look here, it's case 2. Then I call this right away case 2. For the one that is discontinuous from 2 adjacent sides and continuous from 2 adjacent sides, I look here, it is similar to case 4. then I call this case 4. For the one over here, I'm talking about this one for example, it is discontinuous in the short side, then I have to look between cases 8 and 9. Here, this is the short, this is the long, then it is similar to case 9, and then I call it case 9. So now I'm able to know the slab case once I just look at it. Let's take another example. I'm looking, for example, at this one. It is continuous from two sides, the left side and the top side, then it is considered case 4. Okay, and so forth. So this is the first step for me. For every slab that is bound by 4 beams, I have to determine what exactly the case number for each slab. The next step after that is to be able to find what the aspect ratio is. And the aspect ratio simply is A over B, where A is the short span, divided by B is the long span. And remember that A and B are the clear spans, which means if I have a slab that looks like this, bound by 4 beams, then my A becomes that distance, which is the clear one, clear span. Now in the short it becomes A, divided by the clear span, but in the long. Clear span, and that is B. So M becomes A over B, and definitely M is always less than 1, because if it's 1, that means it is a square slab, and A equals B. So now I have those 2 steps. I go to the next step, which is going to finding the coefficients. So I have here coefficients. I bring these coefficients from 3 different tables. Table 13.1, 13.2, and 13.3. We're going to go over each one of them one by one now. The table 13.1 is if you have negative moment. When do we have negative moment? Is when we have continuous edges. If we don't have continuous edges, then it's only positive moments, and then we take a 1/3 of those positive moments on the discontinuous edges. So let's look at it in a little bit more details one by one. If I'm looking at the negative moments, to find my negative moments, which is always at continuous edges, I'll have to calculate it based on the direction. One for the A direction, which is the short direction, one for the B direction, which is the long direction. And anytime I want to find the value of the moment, it's equal to this coefficient, A or B coefficient, times the W, times the length squared. Whether it's A, it becomes, in the negative moment in the A direction, it becomes A squared. In the B direction, which is the long, it becomes B squared. What is W? W is simply your load, and in this case we're using ultimate load, being, for example, the 1.2 W dead plus 1.6 W live. Let's now go to the coefficients A and B. Where do we get them from? For the negative moments, we obtain them from table 13.1. Let's take a look at table 13.1. You'll see that it says table 13.1 coefficient for negative moments in slabs. On the left side here, you will see M. So those here are M's. So once I found M, for example, M equals 0.8, I have to get inside this row and go to the right. Now on the rows, or in the column side, you will see that we have the cases. So whichever case for each one of them, for example, I got case number 4, then I have to go through this column. So I have column and I have row, and then I find the 2 coefficients. What are the 2 coefficients here? The top one becomes CA negative, and the bottom one becomes CB negative. So we have obtained the 2 coefficients to be able to use them in the equation. So once I get these coefficients for the 2 different directions, I see that I just substitute in the equation at the A direction and in the B direction and simply find my moments. What are those moments? These are the moments of the negative moment values for the slab in the A direction, which is the short direction, and in the B direction, which is the long direction. If we take a closer look here into the coefficients table, you will find that some numbers are missing. Why are they missing? Simply because you don't have a value that is equivalent to this. So let's take a look at, for example, case 1. Case 1, there is no negative moment value in all four directions, in A or in B. A on the right side, on the top and the bottom, B on the right and the left, there is nothing, so you'll find no coefficients. For case 2, you have them on all sides, so that means all the coefficients exist. And you will find them having different values depending on the aspect ratio. And then case B, you will find for the B all the time, because B is fixed. And for the A, it's like a pin, so you will have no values for the A all the time. 4, there's always a value on one of the sides. And then 5, there's values in A's, there's no values in B, and so forth. Now we know how to calculate the negative moment values based on coefficients that we got from this table. Remember a very important fact, that this value of negative moment will be from table 13.1. Now when we come to this value, it will be from two tables, table 13.2 plus table 13.3. So we have two values. Then how about this one here? This one will be simply the negative of 1/3 of this value. So now we have the value of the negative moment all the time comes from table 13.1. The value of the positive moment comes from these two values together. We will talk about them in the next slides. And then this one here, which is the discontinuous edge negative moment, coming from the fixity condition of the slab to the beam, but it's not fixed to the next slab because there is no next slab. This is an edge. This one comes from 1/3 of this value. Let's now go to the next part, which is the positive value. The positive moment value comes from, looking here, if I have this as negative, this is my strip, it will look like this, and like this. So this here was the negative that I just brought. Now it's time to look at this value. How much is this value? Say it's two different values. One for the dead load plus another one for the life load. Now the one for the dead load is from table 13.2. And the one for the life load is taken from table 13.3. So you have to take two different moments. One for the dead load positive moment, one for the life load positive moment. And the reason why we split them into two different values is what we call the moment redistribution. The positive moment have a redistribution, and the value depends on whether it's a dead load or a life load. Let's take a look at the dead load first. The dead load comes from table 13.2, and that value will be the positive moment of dead load only, this is the first side, equals the coefficient of the dead load, which comes from this table, exactly the same way. We find M, we pick the case number, and then we pick up the two coefficients. What are the two coefficients? CA and CB. Remember that there's always a number here. Why is there always a number? Because negative moment sometimes is not there, but positive moment is always there. Whether your condition is pin or fixed or fixed pin, there is always a value for the coefficients, and because there's always a value of positive moments in slabs. So we take these values, multiply it by W times A squared or B squared, depending on it's in the direction of A or in the direction of B. Remember a very important fact here, that the W here is only getting from coming from dead load, ultimate load. So the ultimate part of the dead load, which is the 1.2 dead, is what we use with the table number 13.2. Now this is a screenshot of how the coefficient table looks like. Very systematic approach, step by step. We get these two coefficients. We got the first part of the value for the dead load, or for the positive moment. The second part will be the value for the life load. So these are the coefficients of the life load. This is the table for the life load, only for the positive moment. Table 13.3, we go to the case number, we pick up the M, and then we get also two coefficients. Substitute the two coefficients in these two equations, and make sure that your W here is the W for ultimate load only from the share of the life. So it's only going to be 1.6 life. And then substitute with an A for the short direction, B for the long direction, depending on the strip that you're looking at, and then calculate your moments, and then just gather the moment you got from here to the moment you got from the previous slide. You find the total positive moment. Now, important to understand what is the minimum thickness of a slab that is considered a two-way slab. Those minimum thickness come from the minimum design limits of ACI code. If you go there, this nice table illustrates which equations we shall use. This is a copy paste from table 8.3.1.2 in ACI 318, and the value depends on how much alpha we have, and the alpha here is the value that presents the ratio of EI for the beams divided by EI for the slabs. Our target to be able to use this coefficient method is to always have alpha bigger than 2. If we have alpha bigger than 2, that we ensure that there is enough stiffness in the beam to be classified as a beam. And in this case, we're actually comparing these two numbers. The number coming from this equation, we compare it to a 9 centimeters or 90 millimeters. So what is this value? It is simply B, that's the clear span, the clear long span of the beam, open brackets 0.8 plus F yield over 1400 divided by 36 plus 9 beta, where beta is the reciprocal of M, which is the aspect ratio, but rather than short over long, it's going to be long over short. Make sure that you don't make a mistake here when you're calculating beta, because beta is just 1 over M, and this is B, which is here referred to in ACI with Ln, which is the clear span in the long direction measured face to face of the beam. Okay, so we just compare this to 9 centimeters, and that means that the minimum thickness of a two-way slab at any case is 90 millimeters or 9 centimeters. For a slab that has smaller stiffness beams, this jumps up to 125, so 12.5 centimeters thickness, because now we have to depend greatly on the slab to transfer the load directly to the column. Now, as far as reinforcement, we have a minimum amount of reinforcement, and that minimum amount of reinforcement, if we're looking at the slab, we're taking 1 meter width strip of a slab. This is 1000 millimeters B, with the thickness of the slab being H, whatever that H is. Then they found that we have to have some minimum amount of reinforcement within this slab, and that reinforcement should not be less than 0.002 or 0.0018 B times H, depending on the F yield. Let's say that the most commonly used one is the 420 megapascal, and that steel, in this case, we just get the area gross, which is B times H. This is the area gross. And then multiply it by 0.0018 to find the minimum amount of steel needed within that cross-sectional area. Now, going to the spacings limitation, what is the spacing center to center? The minimum is 2H and 450. The maximum is 2H or 250, and the minimum is the regular minimum distance for beams and columns, which is 25 millimeters diameter of the bar, or 4/3 diameter of the aggregate. So these are the two limitations that apply to finding this S distance between adjacent reinforcements. Let's now go over an example that involves calculations of loads, calculation of the thickness, and finding the reinforcement in a two-way slab panel. In this panel, it's actually a corner panel, which means we're just looking at a floor plan that has several floor slabs like this, and we're just taking one of them, which is the corner one. Happen to be 6.5 times 8 on center. So from the center of this beam to the center of this beam, it is 6.5. And then it's bound by 4 beams. Those 4 beams are edging the slab, which is the first nice condition that we have to be able to use the coefficients method. Each of the beams surrounding this slab is a 600 by 600 millimeters in cross section. That's the beam itself. It's carrying a service life load equals 6.5 kilonewton per square meter, uniformly distributed over the surface, in addition to its own weight. So the dead load is basically the own weight of the slab itself. We don't know the thickness. We're going to find the thickness together now. And then F prime C equals 28 and F yield equals 420. Now, how do we solve this? The first thing is we need to find the clear span. When I say the clear span, it means that it is the distance from the edge of the beam to the edge of the beam in both directions, to be called A and B, or LA and LB. Here LA will be the 6.5 minus 2/2 of a beam, so that gives 5.9. And LB or B, this is going to be A, this is going to be B, is the same thing, 8 minus half a beam and half a beam, so that is 7.4. I can simply calculate my M equals A over B or LA over LB. That gives what? 0.8. And then the reciprocal of M, that gives the beta, which we use in the calculation of the thickness of the slab. It's 1 over M equals 1.25. Now going to the ACI equation that we looked at in the previous slides, it's equal to B, open brackets, 0.8 plus F yield, which is the 420 divided by 1400. Make sure that your B is in millimeters, and down here you have 36 plus 9 beta, and the beta equals 1.29. That gives 172.3. As long as it's bigger than 90 millimeters, we're good. We're going to take this number and then we round it. How do we round it? We round it up to the nearest 2 centimeters, so that gives 18 centimeters or 180 millimeters. The second and most important condition is we have to have these beams to be rigid enough to be able to use the coefficients method. How do we know they're rigid? We just simply calculate this factor of height of the beam divided by the height of the slab. We just found the slab thickness here. So that's going to be 600 divided by 180. That gives 3.33. So since it's bigger than 3, then you're okay to use coefficients method. Now the next step is to find my ultimate loads, and those ultimate loads are the ultimate dead coming from the slab thickness just the own weight of the slab. So that's 1.2 times the weight of the slab, which is thickness times the gamma concrete. So that gives 5.18. And then the ultimate life load, which is 1.6 times the life load given in the example, that's 6.5. So that is 10.4. Add them up together to find the total ultimate load of the slab. Remember that the breakdown of the dead end life would be used for M positive, while this ultimate will be used in the M negative calculation. Keep this in mind. Let's take a quick look on how the slab looks like to be able to find the case number, the appropriate case number. Now, those are the cases. I just pulled them out here on this side. To be able to figure out which case number, I need to look which sides are continuous edges and which side are discontinuous. So we have this is continuing to the next slab. This here is continuing to the next slab. Over here is not continuous, and over there is not continuous. They're discontinuous. So in this case, I have here a continuous edge and another continuous edge. If I have two adjacent continuous edges and two adjacent non-continuous or discontinuous edges, then in this case we pick case 4. So this slab, what applies to it is case 4. Let's now proceed with the remainings of this example. Here we picked up case 4 for that slab. My next step is to find the coefficients from the tables. So I go to these tables. I have table 13.1 for negative moment, 13.2 for dead load positive moments, and 13.3 for life load. So this is dead positive, life load positive for 13.3, and this one is the negative moment in the slabs for both dead and life. So this is for the total ultimate. How do I use this table? Let's remind each other. I know that my M equals 0.8. That means I have to look in this row over here. And then I know I'm at case 4. Then I go down this column, so I have these two numbers, 0.1, 0.017 and 0.029. So I pick up those two numbers as my first two numbers in the equation. CA equals 0.071, CB equals 0.029. Those are for the negative values. Now for the positive, I'm pulling out the same exact row. So I go down here and under this column, so I pick up those two numbers, 0.039 and 0.016. So 0.039 and 0.016. And then similarly, I go to the third one down here. I'm going to the row where M equals 0.8. And for case 4, so I pick up those two numbers, 0.048 and 0.020. So those are the two last numbers I pulled out. At this point, I'm done with the tables. I'm just going to use these numbers to start my calculations. Remember that A is the short direction. So when I'm going in the short direction, I have to pick up everything that has to do with the A. Let's put them in this color. So this black color goes to this black color. And then that red color here goes to those three red colors. Okay? So this is how it looks like. Now, how does it work? I have to look at the side where I have a continuity. I put a negative value. And then I go down to positive and then 1/3 of the positive. Same thing applies over here. I have to flip the page at the time I have continuity. I have negative value. And then it goes down to positive and then 1/3 of the positive. It's as simple as this. We have three values to calculate in each side, and those three values are negative moment, positive moment, and then 1/3 of the positive moment to be placed as a negative moment. Then we calculate the moments. This is step number 5. We need to find the positive and negative along the short and long sides. So we're going over to the short direction. Short direction, remind yourself all the time, it's A. Right? Since it's A, then we use the length in my equations as A, which is going to be A squared, right? With the negative, I'm pulling out the number, which is over here. A, I have 0.071, I pulled it here. This is the negative. This is the negative. over here. So it's equal to CA negative times the W ultimate, this is the total load, times A squared. So this is one shot, get one equation, one number, minus 38.52. Now going to the positive, I have to split them into two sides. Whatever I got from table 13.2 and whatever I got from table 13.3. Both of them are A's. So I have to pick up those numbers, 0.039, 0.039, 0.048. One with the dead load, ultimate dead load, one with the ultimate life load, which we just got from the last slide. And then times A squared, pull them up together, sum them up, that gives 24, and that's positive. Now the last one, since it is discontinuous edge, it's simply equal to this value divided by 3. Good, now we have everything for that strip. We can start designing our steel going in this direction. This is for the bottom steel, this is for the top steel above this beam, and this is for the top steel at the edge beam. Now let's go to the other direction. In the other direction, I just flip it and work on that direction. So I have also three numbers. The first number is the negative moment number. Now everything becomes the B. So the B squared, CB negative, same W ultimate. This is the CB negative we just got from the table. This is B squared. I got 24 over here. Definitely much less than the short direction. Why is it less? Because the short direction is a stiffer direction, so it grabs more load than the load in the long direction. Going to the positive moment, I will see that in the positive moment I have two parts, one for the dead load, one for the life load. CB dead, pull that from table 13.2, this one from table 13.3, times W dead ultimate, W life ultimate, B squared, boom, I got the number 15.9. To get this number, I just take the 15.9, divided by 3, put it in negative with a negative sign over in this side. Now I have all 6 moments. I can start designing my slab. We're going to go over very quickly over the design steps. We have bottom steel in the short direction. So I have, here's my short and long direction. Bottom steel in the short direction goes like this. Bottom steel in the long direction goes like this. And then top steel in the long direction will be placed in two different places. We make it in blue now. So top steel in the long direction is going to be this one here. And then top steel in the short direction would be this one here. Of course, we don't forget that the edge top steel also applies, so we put them over here. Now you don't really have to have reinforcement in the top, at the top of the slab, in the middle part of the slab. You don't really have to have top steel, but you have to have bottom steel all over the slab. And then we're going to use number 13 bars. So to use number 13 bars, we have to think about our D. What is the depth of my slab? And then there are two different depths. The first one is for the short direction, and let me explain how this works. In the short direction, if I'm looking at the slab from this side, I'm going to see my bars in the short direction laying out this way. And then I will see my bars in the long direction on top of them. So that means each direction have a different depth, D. Why is this? Because if I'm looking at a strip here, I will see my bars here, taking a closer look, and then on top of them are other bars. So everyone have a different D. This is one D for the short direction, while for the long direction, this will be the D. Then in this case, I have D short, which is equal to HF, the whole thing, the slab thickness, minus the cover, minus half of the bar. So minus the cover minus half of the bar, that gives minus 20. Normally for slabs we have a 20 millimeters thick cover. That's by the code. Minus half of the bar, which is the 13, number 13 diameter is 12.7, so this gives 153. In the other direction, I add another bar. I subtract a full bar. So I'm going from here, zoom in, I'm going from here to here, from the center of this bar to the center of this bar. So I'm adding up another bar over here that gives 141. Somebody might ask this question, why did you put the short direction reinforcement first? And the reason why we do this is because we would like to have our short direction, which carries higher loads, to have the bigger D. And in this case, it provides higher strength, because the more the D, the stronger the section is, and the longer it takes to fail. So you would want that in the direction that carries more load, you have the stronger section to resist with higher moments and so forth. Now, this table summarizes all 6 values that we had. What are the 6 values? Negative moment, positive moment, and then negative moment at the edge, all in the short direction. And then the same thing applies in the long direction. And then we're going over the design steps one by one. It's very efficient as a designer to use tables and then make the tables calculate everything. These here are the equations that we used. Rho required, depending on the M ultimate that we had. And then we have the 3 G's here, and then the 3 B's over here. Rho required is calculated there. And then I go over AS minimum for the slabs, which is the same for shrinkage and temperature. Then I calculated the AS, which is what I obtain from the A required. And then S required, but depending on the area steel. And then we're going over S max. So it's just step by step calculating, depending on the spacing, what's the AS minimum to make sure that it's good. And then calculating the A, lowercase a, and then calculating the C, C over dt, or C over D in this case because it's only one single layer of reinforcement. They're all less than 0.375, so all our fees are 0.9. And then I calculate my phi mn and then provide a layout on how my steel value will end up being. Once I got this, I will sketch my plan with the bottom steel, and then for the top steel, this is how they look like. Now the top steel, remember, they will be placed at locations of negative moments. So they are above the beams, which are the supports. And then for the bottom steel, they are laid out between the 2 supports. So it's laid out between this support all the way to this support. Again, we put this one first, we place it first in construction, and then we place this one. So we ensure that the D that is specified in our design is the same. Now I have a nice question here on the side, says why these values are required values, not the finally selected values. Why is this? And the same thing applies here. And the reason for that is that these are not practical numbers. 36 centimeters is not a practical number to use. 29 centimeters is not a practical number to use. Remember that you would want to pick a number that construction workers don't get confused with. A 29 centimeters between every bar and the next bar is a really inefficient type of spacing that will cause mistakes in the site. So in this case, you can make that 29, for example, comes down to 25 or even 20. That 36 could go down to 30 or even 25. And a lot of times we even unify. So for both of them, we would just pick one number and go with it. And the same thing applies here. The 18 centimeters and the 26 centimeters are not practical numbers. More practical numbers are those who go with 5 centimeters increments. So you go 15, 20, 25 centimeters, and so forth. This concludes this chapter. Hope you enjoyed it. Thank you so much.